Hey everyone, and welcome to this explainer. Today we're putting on our engineering hats to evaluate the absolutely staggering, mostly invisible complexity hidden inside the screens you look at every single day. We're looking at the blueprint for the perfect pixel. And look, this isn't just about pretty colors. This is a deep dive into the complex physics, the microscopic chemical properties, and the massive manufacturing challenges that really govern modern display panels. So think about it. What does it actually take to engineer the perfect display? Whether it's a massive living room TV, a virtual reality headset, or just the smartwatch on your wrist, creating the perfect image ultimately requires us to manipulate light at a microscopic scale. We have to control millions of individual light sources, and we have to do it with absolutely zero margin for error. Okay, let's dive right into this. Here's our engineering blueprint for today. First, we'll cover the physics of the pixel, then compare thin films to vapor deposition. After that, we'll hit the factory floor for precision assembly, tackle the transparent OLED challenge, discuss overcoming lifespan and brightness, and finally, look at the future of displays.
Section 1. Physics of the pixel. The fundamental building blocks.
All right, let's look at the classic physics of a liquid crystal display, or an LCD. At its core, it works fundamentally by blocking light. First, you have a bright, constant backlight being emitted. Then that light hits a polarizer that only lets vertical light waves pass through. After that, it hits a second polarizer that only lets horizontal waves pass. Now naturally, these two perpendicular filters should block all the light, right? It should leave a completely black screen. But right in between them is a layer of liquid crystals. When we apply an electrical charge, these crystals physically untwist, which twists the light wave itself, allowing it to just slip right through that final horizontal filter. By varying that electrical charge, we can control exactly how much light gets through to the color filters.
Now notice how this compares to our other major technology, OLED. LCDs filter an always-on backlight, and since those polarizers aren't, absolutely perfect, a tiny bit of light always manages to escape. That's what leads to those glowing, kind of grayish blacks you sometimes see. OLEDs, on the other hand, which stands for organic light-emitting diodes, completely eliminate the backlight and the crystals. Instead, they use self-emissive organic compounds that generate their own light when a current is applied. Because each microscopic pixel is literally its own little light bulb, it can turn completely off, and that creates true, perfect black.
Section 2. Thin films versus vapor deposition, the manufacturing crucible.
There's just a stark contrast in production here. LCD manufacturing relies heavily on thin film transistors that are carved into glass using photolithography. That's essentially shining light through stencil masks to edge tiny, incredibly precise circuits. OLED manufacturing, though, it relies on a super delicate process called vapor deposition. In a giant vacuum chamber, raw organic materials are heated up until they evaporate. Then, this chemical vapor is sprayed through a superfine metal shadow mask to perfectly coat the substrate.
Section 3. Precision assembly and encapsulation. Welcome to the factory floor.
So let's actually walk through these critical manufacturing stages on the factory floor. It all starts with ultra-detailed substrate cleaning of the glass. The smallest microscopic speck of dust will completely ruin a pixel, so this requires clean rooms magnitudes purer than a hospital operating table. Next is the TFT. Actually, scratch that, it's the thin film transistor layering, which acts as the control center. Then comes that organic vapor deposition we just talked about. And finally, we reach the most critical step of all, vacuum encapsulation. This entire sequence is just a beautifully synced, carefully planned mixture of man and machine operating with unbelievable efficiency.
But okay, here is a staggering manufacturing reality for you. Organic materials instantly degrade when exposed to oxygen and moisture. Instantly. This is why step 4, that encapsulation step, is a massive engineering bottleneck. If that final vacuum seal isn't absolutely flawless, the organic light-emitting diodes will literally destroy themselves the second they touch the air. The engineering tolerances we are talking about here are just mind-boggling.
Section 4, the transparent OLED challenge. The edge case of clarity. To make a transparent screen durable, engineers use something called OCA, or optically clear adhesive. Basically, it's a specialized chemical injected directly between the glass substrate and the OLED panel. Because these transparent panels have an incredibly high manufacturing cost, workers in advanced clean rooms have to assemble these layers with extreme care. The adhesive must be optically perfect, otherwise it completely ruins the illusion of clear glass.
The exact sequence for this transparent assembly is incredibly rigorous. Following the clean room substrate alignment, an automatic machine precisely injects the OCA. But step 3 is really where the magic happens. The panels go into a curing oven. This heat solidifies the adhesive to ensure a strong, tight bond, without a single microscopic bubble ruining the clarity. Finally, the whole panel undergoes strict power, image, and touch testing before leaving the line and eventually becoming that cool sci-fi display in your living room.
Section 5. Overcoming lifespan and brightness. The engineering bottleneck.
Because OLEDs are made of organic, carbon-based compounds, well, they have limitations. They naturally degrade over time. Furthermore, the compounds used for blue light have a drastically shorter half-life than the red or green ones. Because of this, pushing sustained high brightness through the panel actually accelerates a permanent degradation known as pixel burn-in. That's the reason you might sometimes see a ghost image of a news ticker or a battery icon permanently stuck on an old screen. Historically, engineers simply had to cap the peak brightness of these displays just to protect them from themselves.
But capping brightness? That isn't a real engineering solution, it's a compromise. So, enter the micro-lens array, or MLA. This is a microscopic grid of tiny lenses placed directly over the LED panel. Instead of pushing more electricity into those delicate organic compounds, which we know causes burn-in, MLA passively catches the light that would normally scatter sideways inside the panel, and it focuses it straight forward to the viewer. To put the scale of this solution into perspective, consider this. Engineers are packing roughly 5,000 microscopic lenses over a single pixel. 5,000! This astonishing hardware modification boosts the perceived brightness of the display by a massive 60%. And the best part? It does all of that without using a single drop of extra power or putting any additional electrical strain on the panel.
Now, what's really interesting about this next concept is tandem OLED. This is an upcoming breakthrough where engineers literally stacked two completely separate OLED emission layers right on top of each other. By splitting the workload between them, you double the peak brightness. But because neither layer has to work nearly as hard, it actually quadruples the total lifespan of the display. It's just a brilliant, brute force solution to organic degradation.
Section 6. The future of displays. The convergent evolution.
You know that joke in biology that everything eventually evolves into a crab? Well, in engineering, we're kind of seeing the carcinization of displays. LCDs historically had terrible black levels, right? So engineers added thousands of tiny mini-LED backlights to mimic OLED's perfect contrast. OLEDs historically had terrible brightness, so engineers added quantum dots and microlenses to mimic LCD brightness. Completely different underlying technologies are actively evolving to reach the exact same performance goals. They are both trying to become the ultimate perfect display.
But the ultimate evolutionary endpoint, the true crab of displays, is micro-LED. Contrast this with OLED for a second. OLED uses vapor deposition to spray organics. Micro-LED relies on physical mass transfer to place millions of actual physical, inorganic, microscopic diodes onto a board. Because it's inorganic, it never burns in, period. However, physically picking up and flawlessly placing 25 million microscopic diodes for a single 4K TV introduces a massive new manufacturing bottleneck that we honestly haven't fully solved yet.
If we chart this out, the roadmap is honestly incredibly aggressive. Right now, we have micro-lens arrays and quantum dot OLEDs. We are currently seeing tandem OLEDs hit consumer tech. By 2025, we expect highly efficient blue phosphorescent OLED materials to finally fix that blue degradation issue we talked about. But looking 5 to 10 years out, we are charting a course toward true micro-LED, replacing those failing organic blue compounds entirely with inorganic gallium nitride nanorods.
Which really just leaves us with this final thought. As engineers continue to battle the laws of physics, will the ultimate perfect pixel rely on highly refined organic chemistry, purely inorganic mass transfer, or a completely new hybrid of both? The blueprint is still being written. Thank you so much for joining me on this explainer, and keep questioning the amazing technology right in front of your eyes.